Here we have Jeremy. Jeremy is a senior technical writer for Google Chrome. He's focusing on core web vitals and web performance. In his talk, Jeremy will dive into interaction to next paint, ENP, and he will explain how this new core web vital metric works. Ladies and gentlemen, give a warm welcome for Jeremy.
Hey, how's it going? Appreciate it. Hi, thanks for coming to check out my talk here at Heapcon, and thank you to the organizers for making this all possible. My name, as was said, is Jeremy Wagner, and I'm a senior technical writer with the Chrome Developer Relations team, and today I'm here to talk about Google's newest core web vital metric, that is interaction to next paint, or INP for short, but with a twist. Rather than simply going over the metric and how it works and talking about things you can do to improve it on your website, I'm going to be taking a bit of a different tack by focusing on the community's attempts to understand INP issues on their websites and how me and my other teammates at Google's Web Performance Developer Relations team approach thinking about the web performance community's reaction to this metric. So if you're not familiar with INP, your next question is likely, what even is INP? So I'll try to go quickly over how it works. Now, INP is one of the 3 core web vital metrics, and just for fun, in a show of hands, how many people here have heard about core web vitals? That's pretty good. All right, but we still have some hands that are down, so it's worth having a quick explanation of this. The core web vital metrics are metrics developed by the Chrome Speed Metrics team at Google that measure 3 crucial parts of the user experience. First is largest contentful paint, and it measures perceptual loading performance by measuring how long the largest piece of meaningful content takes to appear in the browser. Cumulative layout shift, or CLS, measures how much the layout unexpectedly shifts as a user tries to use a page, which can be a frustrating user experience. And finally, there's INP, which is a runtime responsiveness metric, which I'll refer to as just responsiveness from here on out. And that assesses how quickly a page responds to user input from the time they tap, click, press a key, all the way to the moment that the browser updates the page to show visual feedback as a result of the interaction, which we call the next frame or the next paint. So here are 2 examples of responsiveness in the form of an accordion that you may commonly see on websites. And here we see an example of good responsiveness. When the user clicks on the accordion headers, they open immediately and without delay. It feels reliable and useful without any indication that things feel broken or off. However, here's an example of poor responsiveness. Note that in this version, the user clicks on a heading, but there is a perceptible delay in how long the content below takes to start opening. Because the user thinks the page is broken, they may click multiple times on the same heading, queuing inputs in the order that they were received when the page catches up, potentially causing a frustrating experience. So what causes poor responsiveness? Well, to answer that, we have to talk about tasks. So in order for a web page to provide a user experience, the browser must orchestrate lots of work. And to do that, it uses threads. Most important of these is the main thread. It's where most work occurs, including the work your JavaScript code queues up, or the rendering work required to redraw the page's layout to produce the next frame. So every discrete piece of work that happens on the main thread is called a task. And this visualization is similar to what you might see in the performance panel of Chrome DevTools. And it shows 2 tasks. The one on the left involves evaluating and compiling a JavaScript resource to bytecode so that it can run on the page. The task on the right is from a key up event handler when the user taps a key on their keyboard, or either a physical one or an on-screen keyboard like you'd see on a mobile device. The event handlers bound to that event then run. All tasks that run in the browser take some amount of time to run, and if they run for too long, they can interfere with the browser's ability to begin running pending user inputs or cause rendering updates to the page that take too long. All of this is a source of poor responsiveness. There's a particular kind of task you need to look out for, and those are known as long tasks. Long tasks are those that run over 50 milliseconds, with the portion over that period of time counting as the task's blocking time. In this example, the blocking time for the task is 27.6 milliseconds, which is calculated by subtracting 50 milliseconds from the task's total time to run. The longer a task's blocking time, the more likely it is that the user will perceive that the page is responding slowly to user input. Tasks contribute up to 3 sources of interaction latency, which can affect a page's INP, and each of these sources of latency represents a part of an interaction. The first part of an interaction is the moment of time, the precise moment in time the user begins the interaction to where the event handlers registered for an interaction begin to run. This is known as the input delay, and long tasks from all sorts of sources on the page, such as from third-party JavaScript, can delay interactions from even beginning. Once the input delay finishes, the event handlers for an interaction then run. This total time for the event handler is known as the interaction's processing duration, and long-running code in event handlers can further hold up an interaction from finishing. Where INP is concerned, only event handlers associated with mouse clicks or taps on a touchscreen or key presses are considered. Once the event handler code for an interaction is done, then the browser needs to render the resulting update to the user interface. And we call this the next paint or the next frame, as I said before. This process involves operations such as style recalculation, layout, painting, and compositing. This period of time is known as the presentation delay. And when rendering updates take too long, this can contribute to an interaction's total latency. This process, from end to end, constitutes the entirety of a single interaction's latency. But it can be more complicated. Many interactions consist of multiple event handlers. For example, a keyboard interaction often has both a key down and a key up event. For INP, multiple event handlers that occur as the result of a single user interaction are grouped and known as a logical user interaction. This means that a logical user interaction can have multiple input delays, event handlers that require time to run, and resulting presentation delays. When this is the case for an interaction, the longest event duration of the interaction is measured in the logical user interaction. In this example, the pointer up and click event handlers and their associated input delay and presentation delays represent the interaction's latency. And the INP for a page is calculated by observing all of the qualifying interactions with a page. That is, all tap, click, and key press interactions again. Most often, and for most websites, this will be the single longest interaction on the page. From the moment the browser presents the next frame, showing the visual changes to the user interface as a result of the interaction. Now, there is a small caveat. Some applications, such as single-page applications and rich apps like in-browser games and text editors, have many interactions over the life cycle of the page. In these cases, where there are hundreds, maybe thousands of interactions, the interaction representing the page's INP is not the longest interaction, but rather the interaction that represents the 99th or 98th percentile of interaction duration across all interactions. This is done in cases where there are many, many interactions to discard outliers that may unfairly penalize developers for conditions out of their control. The resulting value in milliseconds is the page's INP. The idea is that by selecting the worst interaction on the page, or closest to it, you have a value that represents a page's overall ability to respond to user input. Think of it this way. If your INP is in the good range, that is 200 milliseconds or less, all the interactions on a page are reliably fast. If your INP needs improvement or is poor, that is over 500 milliseconds, then the interactions on your website might be too slow. An INP is a complex metric, and this is just a quick overview of how it works. To get the full story, you'll want to read the metric doc at web.dev/INP. So as we've rolled out and supported this metric, the Web Performance Developer Relations team has been paying attention to the things the community has been saying about it and the questions that they have been asking. And so a lot of these questions were found from members of the Web Vitals feedback group. It's a Google group that you can join and post to. And if you have questions about INP, or really any of the core Web Vitals metrics, you should check this out because developer advocates from Google consistently respond to every question that people post. And speaking of questions, one really good question we've gotten from multiple people who post in this group is, what do you mean when you say the next paint? And that's a fantastic question. I mean, the phrase next paint is in the name of the metric. But some things you might expect in how the metric determines the next paint may not be as straightforward as it seems. So when we say the next paint, we're talking about the very next visual change that occurs as a result of the user's input. So you might wonder, what if a given interaction doesn't result in a visual change? So let's take this example with two buttons. Both buttons override the user agent styling of buttons in the browser. There's no border, and the active CSS selector is used to override the background color of the button when it is clicked or tapped. On the left, the active CSS selector is used to change the button's background color to red when clicked, but on the right, the active CSS selector changes the background to blue. To the user, it looks like the button on the left triggers a paint, whereas the button on the right doesn't. Is that true? And does INP measure both? The fact is that interaction to next paint measures, as the name suggests, the next paint. And the browser paints a new frame in both of these situations, even if the button on the right renders a new frame that's identical to the previous one. So if you're familiar with the performance panel in Chrome DevTools, you can profile situations like this to see for yourself that this is how INP works. This screenshot is part of a trace that shows profiler data for the video you saw in the last slide. There are two interactions in the interactions track. And the first is for the button that changes color when clicked, and the second is for the button that stays the same color when clicked. Both are registered as interactions that affect a page's INP, even if the interaction produced a frame that was identical to the previous one. And this is because the browser is constantly drawing new frames based on the device's refresh rate, usually 60 times a second. So the name of the metric does accurately describe what it measures. It is the time from the start of the interaction to the next paint it produces in response. But it might be worth thinking about what that means for your website. Maybe one could consider the result of an interaction as the next opportunity to paint. But that's not a very marketable name for a metric because it's very rare that nothing gets painted. So what does that get you? INOP? Sounds a bit like LMNOP. I mean, it gets to be alphabet soup if you're not snappy with it. But even so, the concept is a good mental framing for it because the situations you're going to run into aren't usually going to boil down to things like button styling. That was just a convenient way to show how every paint for an interaction matters for INP. So let's look at a real-world situation of a fetch call, a very common asynchronous operation, and how INP behaves in that case. So here is a video of a demo of two buttons and text areas beneath them, a group of each. So in this demo, each button does the same thing. It fetches a JSON file from the network. It gets a string. Hang on. Let me try that again. In this demo, each button does the same thing. It fetches a JSON file from the network, gets a string of the network response, and dumps it into the text area beneath. But there's one crucial difference between the two of them. The first one waits until the JSON arrives from the network before updating the text area. The second immediately writes a message to the text area before fetching the JSON from the network, and then updates the text area once the response arrives. So you might think one has lower interaction latency than the other, but the fact is that they'd be roughly the same as far as INP is concerned. Asynchronous work and INP is a bit complicated, but the general idea is that an asynchronous operation, such as fetch, is an implicit yield point. The browser does everything it needs to do in the event handler callback up until the async method runs, and then yields or gives control back to the main thread while the async work runs. Once resolved or rejected, a new task is kicked off to run some code in response to either outcome. But the INP, in this case anyway, is not affected by the async work. However, it's best to provide some immediate feedback to the user that something is happening. And this is reflected in what we'd see in the performance panel in Chrome DevTools. This is a trace of the interaction that writes to the text area after waiting for the fetch call to resolve. You can see that the interaction at the left happens and wraps up, which is denoted by the pointer event in the interactions track. The network call for the JSON eventually shows up top, and after it finishes, you can see a teeny bit of rendering work shown in the red circle at the right to update the text area. And this is a trace of the second version, which writes something immediately to the text area before running the fetch, and then overwrites those contents when the fetch call's response arrives. There is some presentation delay incurred to initially update the text area the first time, but the result is largely the same. It just goes to show how nuanced of a metric INP is. Not explicitly painting anything, even if you don't block the main thread, doesn't always mean that you're providing an optimal user experience, especially where async work is involved, even if your INP is good. So this underscores the fact that interactions are your next opportunity to paint. A paint's gonna happen one way or the other, and will take as much time as it needs, but where async work is concerned, where users could be left wondering if things are working, paint something, but paint something useful. So that brings me to another thing. We've occasionally found with some limited instances with Core Web Vital metrics where they can be cheated. We address these problems as soon as possible when they come up. For example, we changed LCP to ignore when low entropy images paint, such as solid colors or blurry placeholders, because these types of images aren't valuable user experience signals. So I don't like to make sweeping statements about nuanced things, but everything one could do to try and cheat on INP falls into one of two categories. One, you're doing something that improves interaction latency and paints can happen faster, stuff like breaking up long tasks or doing less work. Or two, you're doing something that ends up being a bad user experience signal, and even if it does improve your INP, it could be an anti-pattern that is not good for the user. So paint something as soon as you can, but make sure whatever you paint is useful. So a recurring thing we've seen in questions from the community is the nature of page links, the humble A element, to be specific. And it's a curious sort of problem because you might think these elements wouldn't tank your website's INP, but they can be a source of high interaction latency. So if you've got some A elements on your page behaving badly, you might want to consider some of the following causes. So, say you have event handlers in your own code that run when a link is clicked. That could be a source of problems. Check to see if you have such code bound to links in your application, and see if you can minimize that work somehow or break it up. But also remember, third-party scripts such as analytics, tag managers, and tons of other possible sources can do damage too. In particular, check your tag manager settings to see if you're loading unused code and tags that could be doing work that you no longer need to do, and remove that stuff. You have to clean up every now and again. Another, are you running a before unload event callback with a prompt such as alert? Not so fun fact, such prompts are synchronous and block the main thread until they're dismissed, meaning that if a user takes a long time to dismiss it, your page's INP could be thousands of milliseconds long, which is not great. And for a variety of reasons, before unload prompts are discouraged. For example, these event types can make pages ineligible for the back-forward cache, which is a mechanism that stores previously viewed pages and their state in memory so that they can be instantaneously loaded again if needed. So the bigger point here is that in terms of general performance advice, you probably want to avoid using before unload unless you absolutely can't help it. Another cause are SPAs, which override default link behaviors to perform what we call soft navigations. That can run a lot of work to update the rendering of the entire page when you navigate to another page in the SPA's framework. While all navigations have the potential to kick off lots of rendering work, the concept of detecting soft navigations in browsers is currently an experimental feature under development. For now, for the purposes of INP, a single page navigation can potentially capture all of the interactions that occur during the user's session with the page, or with the entire website in this case, which may make INP more difficult to optimize for in such applications. So, another interesting thing from the community is the concept of yielding. Now, I've talked about breaking up tasks, and yielding is how you do it. Yielding is a mechanism that allows you to pause execution of a currently running task and yield control back to the main thread to allow other higher priority work to run before resuming the paused task. So in case you're not familiar with yielding, one thing you should know is that the browser always eventually yields when a task finishes. This is something we like to call implicit yielding, where a task will run as long as it has to in order to finish before giving control back to the main thread to run the next task. However, you can explicitly yield in JavaScript, and this lets you break up long-running tasks without having to wait. At top, in this visualization, a long task runs and no explicit yielding occurs. This means that a user input was received as the task runs, and it has to wait for this long task to finish before running the interaction's registered event handler callbacks. At bottom, however, a task is broken up by explicitly yielding every so often, meaning that the user's input waits for less time to pass before running event handler callbacks to process the interaction. This works because in Chromium-based browsers, interactions are given a higher priority than tasks from other sources, so they go to the front of the task queue. Now, yielding has traditionally been done with a few APIs that weren't designed for this purpose. One is set timeout. And set timeout is effective because it schedules a given callback in a new task. You can make this more ergonomic by way of this little helper function we call yield to main, by wrapping it in a function that returns a new promise and then passing the promise's resolve callback to set timeout with a delay of 0. Because this yielding function returns a promise, it can be awaited inside of an async function. And here you can see that, well, in an implied fashion, since this code snippet omits specifics, that a piece of work is done, we then explicitly yield control back to the main thread, and then we continue on with our work. But there are other ways to yield. More importantly, there are other times that you can yield. So here's a bit of a different pattern that we've discussed with the community, where the yield point created using set timeout is placed inside of a request animation frame callback, which we call yielding after the next paint. This explicitly postpones work after the yield point until the next frame. And this works because request animation frame sets up rendering work needed for the next frame. So it's the last thing to happen before the frame ends and the rendering work for the next frame begins. So using this, you could do some critical work that updates the user interface first, for example, but then explicitly end the current frame to allow rendering, then resume the remainder of the work after that point. Is this better than the other way to yield, where we just split up tasks whenever we want, without any regard to whether the current frame is or should be ending? It might be. It might not be. As with every other engineering question, the best answer is, it depends. Request animation frame callbacks adhere to a concept known as vsync, where rendering updates are synchronized with the display's refresh rate. And this means that in practice, you can't render more than 60 frames in a given second on a typical device. Note the word typical, as other devices may have different refresh rates, but 60 FPS is the most common you'll encounter. So if you try this yielding approach often with lots of small bits of work, you'd actually be delaying all that work from getting done sooner, as each frame would have a relatively large gap where to allow the browser to decide when to draw the next frame. Whereas if you use yield to main, you're providing opportunities to render, but you're not fixing them to have to wait until the next frame begins. So you can batch things up a little bit better. Say, you might overshoot your budget for a frame, 16 milliseconds and some change in this case, but you'd be well within your budget for IMP at 200 milliseconds or less, just so long as the work you did prior to yielding didn't go way over the line. By contrast, if you use the after next paint idea, where you could defer work until the next frame, you could find yourself in a position where you do a itty-bitty little bit of work, say something like 2 milliseconds or less, otherwise far less than the long task boundary of 50 milliseconds, and find yourself just wasting time until the display refreshes to give you the next frame where you can resume the remainder of the work. However, you may have some work that runs for a bit of time, and that may be just the kind of thing that's worth using the after next paint pattern for. I won't tell you which to use. Both patterns have their uses in specific situations, so it's not a one-size-fits-all type of thing, and the drawbacks are both being addressed by new browser APIs anyway. So, are there downsides to yielding? Should you yield all the time? One concern we've heard from the community is that yielding with set timeout can put you to the back of the task queue. And so this means, by you playing nice, you lose out to other tasks, particularly those scheduled from third-party scripts, which may not play as nice. Scheduler.yield, which landed very recently in version 129 of Chromium, addresses this problem. Continuation is the concept of yielding, but keeping you at the front of the task queue so that you don't lose out, except to really critical tasks, such as painting a frame or user interactions. In this diagram, we have 3 scenarios. The first is without explicitly yielding at all. A task will run as long as it runs, sometimes too long, and once it finishes, an input and subsequent render can be queued, and the next scheduled task runs. In the second scenario, you can break up execution of a task with set timeout. However, after high priority tasks such as handling input or rendering, a task from another source can schedule tasks ahead of the remainder of the work you needed to finish after you explicitly yielded. The third scenario, you break up execution of a task using scheduler.yield, which preserves the intended order of task execution, ensuring your work does not block inputs and rendering, which should be higher priority, but ensures that your work is ahead of other queued tasks from other task sources. So Chrome has been working for a while to solve this problem, and scheduler.yield goes a long way in that effort. Like our previous example with yield to main that uses set timeout in a wrapper function that you can await, you can use scheduler.yield in much the same way because it returns a promise in order to yield to the main thread. So the implementation and how you would use it looks pretty similar, but you get the benefit of continuation when you use scheduler.yield instead of using set timeout. So here's a little demo on scheduler.yield and how it contrasts with set timeout for yielding. This demo, when the top button is clicked, and it was already clicked in both of these demos, runs a bunch of blocking tasks using set interval. So when we click this button, as seen in this demo, we run a bunch of blocking tasks in a loop, and when we yield with set timeout, we yield with set timeout on every iteration of that loop. You can see that every time the page yields with set timeout, the remaining work gets interrupted by tasks being run periodically by set interval, and this is an example of a lack of continuation. You can see that processing loop item 1, 2, oh, set interval comes in, and then so on and so on. Now here's the same demo, but rather than yielding in the loop using set timeout, scheduler.yield is used instead. And so you can see here that after yielding on each iteration of the loop using scheduler.yield, it is ensured that the remainder of the work the loop needs to do goes to the front of the queue, ensuring that tasks run by set interval don't cut in line. Scheduler.yield means that your work is what gets prioritized aside from user interactions, which are higher priority. But that work from other task sources runs afterwards. And here we are. I hope this talk gave you some insight into not just IMP, but how key responsiveness is to the user experience. Naturally, though, you'll have some questions about where to go next. And you might be curious to know how your website's core web vitals are and how they're doing according to its real users. And so for those who opt in, Chrome collects telemetry data, including for core web vitals. And if your website receives enough traffic, you can get origin level data from your users, and even page level data in some cases if you have enough traffic on specific pages. It's a great starting point for figuring out if your site's core web vitals are bad or if they're good. It doesn't tell you how to fix things with your core web vitals if they're bad, but at least you'll know where you're at, and that's worth something. Finally, once you know what your website's core web vitals are, and how they're doing, if you need to do any work or not, you can either build your own solution for collecting field data. Field data is data that is collected from real users, or outsource this work to a real user monitoring provider, including advanced diagnostics that can help you pin down precise causes of slow interactions. And this information and an accompanying code lab is available in the form of a video I shot for Google I/O on demand this year. You can search for it on YouTube if you Google new field insights for debugging INP, and you can check that out. And once you got the scent of the trail, the next step is to go about fixing INP. And it's a complex, sprawling subject matter area, but we've launched a content collection last year on web.dev covering many aspects of INP and how you can go about troubleshooting and fixing common causes for different parts of the interaction, all the way from the input delay to the presentation delay, even including things like how does script evaluation get in the way of user interactions, that stuff that happens when a page is loading and JavaScript is downloading and being compiled and executed and all these things that are important and how they could actually affect runtime responsiveness on your web page. And with that, and I thought I would go way over time, and I did not. Thank you for coming to my talk. I had a blast giving it, and I hope you found it useful. And if you see me in the hallway, please don't hesitate to stop and ask questions. There's likely something I didn't cover that you might be curious about, and there's a lot of stuff about INP, and web developers are a really curious, intelligent bunch of people. You will likely have thought of something that I might not have thought of. If I know the answer to your question, I'm happy to help. And if I don't, I'm happy to point you in the right direction. So please, if you see me out there, come and flag me down. We'll hang out, we'll talk about it. The hallway track is one of my favorite tracks. cheers. Thanks for coming, and keep it snappy.
Thank
So
you.
we got 5 minutes.
Yeah, thank you, Jeremy.
I would wonder if we shouldn't do a little Q&A.
Yeah?
Yeah, let's do it.
We have a question here.
Oh, yeah, the microphone would be good. I can't hear it that well. It's all that heavy metal music.
Hi, interesting presentation. So I wanted to know, you mentioned like it's usually 60 frames a second. That's the view is refreshing the screen rate. But
Sure.
how do you handle the cases for adaptive refresh rates? Like some phones can go as low as 1 frame per second.
Right. So browsers, so I'm just a disclaimer, I do not work on the rendering team. But as far as I know, browsers do adhere to VSync. And I'm not exactly sure how they accomplish this in cases with active refresh rates or like variable refresh rates. But VSync is very much a thing in web browsers. So generally speaking, whatever your device's refresh rate is kind of what you're working with. And if it isn't a active, if it isn't a variable frame rate, the browser will definitely try to produce frames on some interval or some predictable interval. So generally speaking, the mindset when you're going to optimize INP, if you're worried about presentation delays in rendering updates, having a mindset of a fixed frame rate is what we would recommend for developers to target.
So simplify to it being basically
Sorry?
that we should simplify to it being constant, not changing basically.
Constant. Generally 60 frames per second or capped to whatever the refresh rate is, but commonly 60.
Okay, thanks.
Thank you. Do you have any additional questions?
Anybody else?
I got 3 minutes. Oh.
Hey, great
Hey.
talk. Wanted to ask, does IMP work with Canvas? Like, we have a Canvas, like we built a video editor, and we draw at like X frames per second using request animation frame. Like, can it detect changes on the canvas based on interactions?
That's a good question. I am certain that this is a case that has been thought about because the registered event handlers would be typical to the browser. It would be things like mouse down or click. I actually don't know the answer to this question, but I do know that some of the partners we worked with have canvas-driven applications, and that IMP is a factor with that. But I can't give you a precise answer in this case. But I could. I know the right person to ask on the rendering team, so I can ask that question. And if you see me in the hallway, please get in touch with me, and I can give you the answer. Everybody is very busy at Google right now. I'm getting lots of messages, so I'm sure somebody will answer that immediately. But sorry that I don't personally have a detailed answer. Sorry.
Sorry, I have no voice. I was singing.
No worries.
What would be some of the examples of the useful elements we can show? You mentioned them, the useful elements that we can show. Could you give us some examples? Like, what could it be not to disrupt the user experience?
So you're referring to when I was talking about like the fetch call thing. Yeah. So when I say paint something, but paint something useful, a good example is anytime there is a user interaction which results in some kind of asynchronous work, is to show some kind of user interface indicator. So like spinners are often overused, but a spinner is better than no spinner, because if you click add to cart, well, that's got to make a call somewhere, and that might take a while. It could take a few seconds. Even just doing something like graying out a button, say like add to cart, click it, gray out, and then change the button text to say adding to cart, can be a good signal. It really depends on the specific application, but literally any signal you can give a user that makes sense to them, that something is happening, is better than not doing anything at all. Like saying click add to cart, and they're like, why isn't this working? and then turns out they added to cart like 5 times, right? So, that's why you should do that. And I had another thought, and it's gone. It's gone. Sorry, it's gone. Yeah, it's specific to the user experience like that you're trying to provide, but literally anything other than doing nothing. Like if they just click and nothing happens, they'll probably think it's broken, even if your INP is good. So yeah, I feel like I got some good questions here. So yeah, thank you. We're out of time. So.